I am Dr. Nitisha Shrivastava. Welcome back to the control system lectures. This lecture is for steady state error and the error constants. Now, as we have seen that the steady state error is an important performance indices as related to the time domain specifications of a second order control system when subjected to a unit step input. Now, here in this lecture we will understand that what would be the steady state error when there are different types of inputs and also as related to the type of the control system. So, steady state error is the difference between the output and the reference input in the steady state. In real world, because of friction and other imperfections and the natural composition of the system, steady state or output response rarely agrees with the reference. That is, what is meant here is, now we expect a certain value of output as desired output, and achieving that desired output is actually not very easily attained, just because that the real world is having many imperfections and the natural composition of the system. There are various elements in the system, and due to the various elements on the system, the obtaining the steady state value or obtaining the desired value is not very easy. That is, the steady state errors in control systems are almost unavoidable, and steady state errors of linear control system depend upon two quantities. As I said, it is dependent upon the two quantities. One is the type of the system and what is the reference signal. Reference signal means whether it is a step input, whether it is a ramp input or a parabolic input, because different test signals are applied to a control system to check the response of a system for different kinds of input. So, that becomes the reference signal, and what is the type of the system we will understand now. Now, to understand the type of a system, what do you mean by type of a system? We are going to consider a control system with unity feedback. R of S is the reference input, E of S is the error signal, and C of S is the output. G of S is the forward path transfer function. Forward path transfer function is GS, and H of S is 1 here. So, H of S is 1 since it is a unity feedback system. So, what is the output C of S? C of S is equal to the forward path transfer function multiplied by E of S. And what is E of S? E of S is the output of this summing point, that is the difference of the signal. C of S is the input given here, and it is compared with the reference signal R of S. So, E of S is R of S minus C of S. Basically, it is R of S minus C of S. And what is C of S? It is the forward path transfer function multiplied by E of S. Substituting the relation, we get E of S, that is the error signal. It is the difference between the reference input and the output. Therefore, it is known as the error signal, and manipulating, rearranging the terms, we get E of S, that is the error signal value is R of S upon 1 plus G S. Here H of S is 1, otherwise what would be E of S? E of S would also have a term H of S, and here we have replaced it with 1, that is H of S is 1 since it is a unity feedback signal. So, our output R of S is equal to 1 plus G S. And how is steady state error of a system written as? steady state error is the difference of the reference input and the output when time reaches infinity. So, in S domain, following the limits, limit S tends to 0, that is the final value theorem, operating on the final value theorem, the steady state error is equal to limit S tends to 0 S E S. This comes from the relation of final value theorem. And what is E S? E S is R S upon 1 plus G S, that is the G S is the forward path transfer function and R S is the input, that is the reference signal given to the forward path transfer function. Therefore, the value of steady state error as limit tends to 0, S tends to 0, S into E S. So, as we can see that the steady state error is dependent upon the reference input R of S. Now, what do we know by type of the system? What is type of the system? Type of the system is number of poles G of S has at S equal to 0, and that decides the type of the system. G of S is the forward path transfer function. Now, for example, G of S is 10 S plus 2 upon this denominator. Here you can see that there is only one pole at origin. S is equal to 0 means the pole number of poles at origin. If the number of poles at origin is 0, then it is a type 0 system, and number of poles at the origin is 1, then it is a type 1 system. Here we can see that there is one pole, there are poles at -1, -3 and poles related to this quadratic equation, the second order equation, and we can see that there is one pole at the origin and therefore, it is a type 1 system. In type 3 system, here we can see that this G of S in the numerator has S plus 3, that is there is 1 0 at -3, that is the negative real axis, and there are 3 poles at the origin because S raised to 3. So, as many poles at the origin decides the type of the system. So, the type of this system is 3, whereas the order of the system is 4, because when you multiply this, it is, this becomes 18 S plus 3 S raised to 4 plus S. So, the order of the system is 4 and the type is 3. So, the number of poles at the origin decides the type of the system. Here it is a type 3 system. Similarly, if you have, for example, G of S is equal to 18 upon S square S plus 1. This is a type 2 system, whereas the order of the system is 3. So, therefore, steady state error depends on what is the characteristics of G of S. We know this relation because steady state error has a term G of S. So, characteristics of G of S, that is what is the transfer function, forward path transfer function, and the number of poles G S has at S equal to 0, and what is the reference input. What is steady state error with step input function? Now, for a step input function, R of S is 1 upon S. Now, we will understand in the further lecture how the type of the system and the reference signal are related as to the steady state error of a system, because steady state error is S into G s upon 1 plus G s. So, there is a term S in the numerator. So, type of the system affects the steady state error as well as the reference input signal given. Now, we will study this for a unit step function, and we will study this for a ramp function as well as parabolic function. We will understand what would be the steady state error when different inputs are given for a different types of the system. So, when the function is r of t, that is for unit step function or just a step function, we are taking a magnitude r upon s. R upon s is the unit step function having a magnitude r. It means simply that this is a unit step function with a magnitude r. This is the time axis and this is the signal r of t. Now, ESS is equal to limit s tends to 0 s r s 1 plus G s. Here we can see that since r of s is r upon s, the term s and this s cancel out. So, therefore, the numerator has r and s tends to 0, this 1 limit s tends to 0 is applied to G of s. Since s in the numerator has cancelled out due to the presence of reference signal as the step function, and this limit G of s tends to 0 is replaced by a term K p. K p is termed as the step error constant. Since we are talking about the step input, this constant K p is termed as a step error constant. K p equal to limit s tends to 0. Now, for a type 0 system, type 0 system means G of s does not have any pole at s is equal to 0, that is there is no pole at the origin. When there is no pole at the origin for a type 0 system, K p will always have a finite non-zero value, because we can see that limit s tends to 0 G of s is K p. Now, if this G s is a type 0 system, like for example, s plus 3 upon s plus 4. So, this is a type 0 system, and for type 0 system always the constant K p will have a finite constant value, because we are not having any poles at the origin. Therefore, the denominator of G of s will not have any term s in the denominator, that is no poles at the origin. Therefore, for a type 0 system, K p is always having a finite constant value which is non-zero. For type 1 system, what will be K p? Now, for example, G of s is a type 1 system. Type 1 system s plus 1, for example, G of s is equal to s into s plus 1 upon s plus 3. So, this is the type 1 system. In type 1 system, there is a pole at the origin, only one pole at the origin. So, if you have one pole at the origin and in G of s, when you take s tends to 0, so your K p becomes infinite. That is, for a type 1 system, K p is infinite, and therefore, the steady state error is 0 for a type 1 system when subjected to a step function, step input. Similarly, for type 2 system, K p is infinite since G of s has two poles at the origin. For example, the same we can take G of s is equal to s plus 1 upon s square into s plus 3. This is a type 2 system because there are two poles at the origin, and when s tends to 0, G of s is solved, we get the value as infinite. Therefore, the steady state error is 0. So, what is the conclusion out here when you summarize the steady state error for step input function subjected to unit step input, what happens? The type 0 system, as we have seen, for a type 0 system Kp is always a constant value, therefore, steady state error will also be a constant value. And for type 1 and higher systems, since the step error constant Kp is a constant value, is an infinite value, therefore, steady state error will always be 0. And for steady state error to be 0, then we can say that Kp must be infinite for a step function, that is a step error constant, and for Kp to be infinite, g of s must have at least one pole at the origin. So, this means that when the system is subjected to step input and it is required that the steady state error be 0, then the system should have at least one pole at the origin. Now, steady state error when subjected to ramp input function. Now, what is a ramp input function? When the reference input is a ramp function, then we can say that with a magnitude r, this is a ramp function. Now, we will find the steady state error when the system is subjected to a ramp function. So, what is E of s? E of s is limit s tends to 0 s E s, and what is E s? R s upon 1 plus G s. So, what happens now when we are applying a ramp function? What becomes ESS? ESS is, this is R divided by ESS is equal to limit s tends to 0 s r upon s square divided by 1 plus G s, that is, sorry, this is equal to 1 plus G s, and since we have this, okay. Now, only the term s cancel out, we have a s in the denominator. So, that is s into s G s. So, when you are applying the limit s tends to 0, this quantity becomes 0, and limit, since g of s is a transfer function, here limit s tends to 0 s G s. This quantity is termed as the ESS now is R upon kV, and this kV is termed as the ramp error constant. As we had seen, the step error constant is defined here, limit s tends to 0 G s, whereas the ramp error constant is kV, limit s tends to 0 s G s. Now, for a type 0 system, what is the value of kV? For the type 0 system, kV will be 0. Type 0 system means, like for example, g of s is equal to s plus 1 upon s plus 3. This is a type 0 system, and in type 0 system, when you substitute this, we get it as kV equal to limit s tends to 0 s into s plus 1 upon s plus 3. So, in this case the ramp error constant will always give you a 0 value, because there is a term s in the numerator. So, when you apply a ramp input for a type 0 system, the ramp error constant, that is the velocity error constant, will always be 0, and therefore, the steady state error will be infinite. Now, for type 1 system. For type 1 system, kV will always be a finite value. Let us take a type 1 system. In that case, G s for type 1 system, it is s plus 3 upon s square into s plus 2, not s square, it is a type 1 system. So, it is not s square, it will be g of s is equal to s plus 1 upon s into s plus 2. Now, in this case we can see that when SGS is evaluated, this type 1 S in the denominator will always cancel out with the term S present here, and therefore, ESS will always be a constant value, because KV will be a constant value for a type 1 system, and therefore, the steady state error will always be a constant value. Now, for type 2 system, in type 2 system the denominator has, the G of S has 2 poles at the origin. When there are 2 poles at the origin, then we can see that when you evaluate G S, so what will happen to KV? KV is equal to limit S tends to 0 and S into S plus 1 upon S square into S plus 2. For example, this is a type 2 system and we are calculating the value of the velocity error constant, which is also known as the ramp error constant. In this case, 1 S will always appear at the denominator. When this appears at the denominator, it means that KV will always be a infinite value for a type 2 system, and therefore, what about the steady state error? Steady state error will be 0. So, we are just summarizing what we have discussed just now. As we had seen that for type 0 system, ESS is always an infinite value because KV will be 0, and for type 1 system, ESS will always be a constant value, and not for higher systems, it is only for type 1 system, ESS will always be a constant value, and for type 2 and higher systems, ESS will be 0. So, for we can conclude here, for steady state error to be 0 when subjected to ramp input, when ramp input is applied, and we expect the steady state error to be 0, and that is obtained only when the type of the system is 2 or higher, because for type 0 system the steady state error is infinite, and for type 1 system it is constant, whereas for type 2 system the steady type 2 and higher systems steady state error will be 0. Or for type 3, if type 3 is considered, we have 3 poles at the origin. So, still 2 poles appear at the denominator of G of S, and in that case KV becomes infinite, and therefore, ESS will be 0 for all the control system types which are greater than 2. Now, when the steady state is when the control system is subjected to a parabolic input, what will be the steady state error? So, as we have seen, it is ESS is equal to limit S tends to 0 S into GS, S into ES. So, it becomes SRS upon 1 plus GSSS. So, here it is R upon S cube is the reference input here. So, replacing R of S, we have S square in the denominator. So, ESS applying limit S tends to 0 will give 0, and this term is known as the parabolic error constant and is given by the relation Ka. Ka is equal to limit S tends to 0 S square Gs. Now, we will do the analysis for type 0 system. Now, we understood what is a type 0 system. Type 0 system means there are no poles at the origin, and when there are no poles at the origin, what happens? There is a term S square always appearing at the numerator, and when this appears at the numerator, definitely Ka will be 0, and steady state error for the condition when the input is a parabolic input, ESS will be infinite, that is the steady state error will be infinite. For type 1 system, since we have s square in the numerator and type 1 system has one pole at the origin. One pole at the origin means, that is, let us take a type 1 system and what do you find the value of K A, limit s tends to 0, s square s plus 1 upon type 1 system has only one pole at the origin and the denominator could be s plus 1, s plus 2, s plus 8, anything. The order of the system could be anything, but the type of the system is 1, that means there is only one pole at the origin. Therefore, the numerator will still have one term s remaining in the numerator and therefore, K A will always be 0 and in that case ESS will be an infinite value. For type 2 system, there will be two poles at the origin and when there are two poles at the origin, there is no s term, that is in the numerator and therefore, K A will always be a constant value and in that case the steady state error will also be a constant value. Summarizing, it is not higher, please strike out this, ESS is infinite. For type 0 system, we can see that ESS is infinite. For type 1 system also ESS is infinite, whereas for type 2 systems it is constant and for type 3 systems and higher it becomes 0. Yeah. Therefore, for steady state error ESS to be 0 when the input is a parabolic function, K A must be infinite and for K A to be infinite should have at least 3 poles at the origin, because when you have 2 poles at the origin you get a constant value and when there are 3 poles at the origin, this means that it is s square s plus 1 upon s cube into s plus 3. So, in this case one s appears at the denominator and therefore, K A becomes infinite and ESS becomes a 0 value. Therefore, for type 3 and higher systems ESS is always 0. So, this is the summary related to parabolic input. So, for example, we have just taken the graphical representation here, the summary of the steady state error. This is the step function and what is the steady state error? Steady state error is R upon 1 plus K P. Steady state error as defined here is R upon 1 plus K P, that is what is mentioned here. ESS is R upon 1 plus K P. There is a difference between the reference signal and the output of the control system. This is a ramp function, we can see that this is a ramp function and the steady state error is given by the relation ESS is equal to R upon KV, where KV is a ramp error constant or also known as velocity error constant. Similarly, Kp is known as a position error constant or displacement error constant or also as a step error constant. This is velocity error constant. Similarly, for a parabolic function, this is a parabolic input, the input is parabolic and the error is given by ESS is equal to R upon Ka. So, this table summarizes the different values of error constants. Now, we can see that in this table it is listed type of the system as well as error constants and the steady state error. If the type of the system is 0, then Kp is having a certain value, whereas Kv and Ka are 0, and for type 1 system Kv is having a constant value, and for type 2 system Ka is having a constant value. And what is the value of the constant? It is r upon 1 plus k, and here it is r by k, and this is r by k. So, this table summarizes the error constants for different inputs. Since error analysis relies on the use of final value theorem, this care has to be taken to check the location of any pole on the right half S plane, since the entire value of the steady state error is dependent on the final value theorem. So, it is important to check first to see if SES has any poles on the j omega axis or on the right half of the S plane. Thank you.